which is this one. Okay. So what I'm trying to do, which is taking time, but you know what I'm trying to do, is the following. I'm writing the slides. From where? From the book. So since I'm writing the slides from the book, that means that probably, you know, some mistakes, some errors, some typos, something, okay, it should be correct. Okay. So that means that, you know, I am in the process to transform the book into slides. Okay? So, I mean, I have some slides, some others I don't. Okay, so it's dynamic this year at least. So yesterday we finished about, you know, looking at the matrix derivative, and today we make another hint about this. Now the next hint is that, you know, we can have matrices that are composed by complex valued entry, okay, which is a complex matrix. So, you know, you might say, and you would be correct, that a complex number is just the two numbers put together. Now, so if you have a complex number, actually, you can take a real part and imaginary part and then stack the two entries into a 2 times 1 vector. Everything that you are going to do in this way is formally correct. So in most of the cases, you know, we try to avoid to write complex numbers, complex value, okay? Real imaginary. But you know, if we can't, we try to find a way how to handle the complex numbers. So this is some, you know, some insight on that, as I try to give you now. Okay? And you know, rather than say just aseptically, I can write a complex number as pairing to real and imaginary. I do it in a multidimensional way, which is by a vector of n dimension. So let's consider the case of the n-dimensional complex valued vector, which means a vector composed by complex numbers. Okay. So this vector is a vector x, which is written, you know, as conventional way as a vector. And this vector is composed by n numbers. So if you have your data, your experiments, now where these experiments are coming, you say, I cannot measure the complex number. Okay? So if someone say, I am measuring complex number, technically you cannot, because you don't gather complex number. Complex number is, you know, is a very convenient representation, for instance, for narrow band signals. So if you have a narrow band signals, the complex valued representation is very convenient. Okay? And then, you know, all the telecom should very well know why, you know, you use a complex number, because it's a real and imaginary part is the mapping of an in-phase and component of a signal, okay, of a narrow band signal. So once I say that, for all the others which are not telecom, okay, so there are problems where someone, telecom, prepared the signal to be complex. Okay? So in this case, you know, you need to say, well, how you can manipulate the data, how can you manipulate the vector. Now, a very convenient way is to write the two set of numbers as one vector of real and the other vector of imaginary part. So in total, remember, if I have n complex numbers, in total I have 2n numbers, because it's n numbers as real and n numbers as imaginary. Okay? So I indicate that these two set of numbers, which is a vector composed by n real numbers and a vector composed, sometimes I indicate in this way just to indicate that it's a vector. So the vector composed by n numbers and the vector composed by imaginary numbers, okay, they are belonging to the set of complex valued vectors which are composed by n numbers, and it's indicated this way. C indicates the complex field. Now, as an alternative way, I can rewrite, as I said, you know, the complex number as a real and imaginary. So what they do, I indicate in this way as an x tilde. So x tilde actually is a vector of length 2n, where in the first part I include the n component, which are the real part, and the second part is the imaginary component, which is n. So the total vector is 2n because it's just a stacking. Stacking means put on the top of the other the real and imaginary part. Can we open the door? Yes. Don't you feel hot? Okay. But this one is closed, right? Thank you so much. You can use the bike. Doesn't stay. Use the desk. So the bike has a sense now. Okay. Engineering attitude, solve the problem with nothing. Because when you go in a company, you are asked to solve complicated stuff, but you have no money. So this is once you are finished with the degree, okay, your struggle will be that you are asked to do something and you have no money. They give you no money, okay? Or you are asked to do a complicated system and you have no, colleague, you have nothing, okay? So you need to invent. Anyway, so let's go here. So, this is the vector x tilde. Now, actually, x tilde is different from x because, it's not only because x contains real and imaginary, and the size here is n, and this one is 2n. But now, this vector and the other vector are fully equivalent because they have the same information. Now, since when we discussed up to now, we said that the numbers we are considering are real. So, if we want to go back to all the theory that we are going to develop, is simply take the complex number, take the complex vector, and write it as a real. You can rederive every theory, any theory, whatever. So what I'm saying now is take these words and extend to the end of the semester. Okay. So you can take, a real vector composed by 2n entries, and then you rederive everything. Now, so let's consider a very simple case where x is a complex with a scalar, so n is equal to 1. Okay. So I have a scalar function, okay, and let's consider that I have a function phi of x. Now this phi of x, is mapping a complex number into a complex function. Okay, so this is the mapping C to C. That what I can do, I can write similarly, in a very similar way, a different function which is h, that is working on a vector x. And now this vector x is composed by 2 entries, the real and imaginary. So this is what I indicate here. This x tilde, this is not the first, so this is left means I'm breaking, okay? So it's another case. So this x tilde is composed by 2 scalars, so it's x real, x imaginary, okay? So this one now is 2 times 1, okay? So, it's exactly the complex number. Now, so, in this case, these real, so which means the 2 numbers, is mapping onto a complex, okay? Similarly as before. Now, this function h, which is technically just composed by the real and imaginary part, should be equivalent with the other, because it's just a different representation. But I know how to calculate the derivative here. I don't know how to calculate the derivative there. So let's see how I can write it, how I can make the derivative. Okay, so I can write a derivative of a 2 times 1 vector, okay, which is something that I know. And then I can make the correspondence, which means the total equivalence, with a derivative that I might compute onto phi. Now, so since I have this mapping, okay, so I can define a function which is composed by 2 entries. The variable is x and x star. Now, if I write this function that depends on x and x star, is still the same as 2 variables because it's the variable and the complex conjugate of the same variable. So if I want to get the real part, I take x plus x star, okay, divided by 2. If I want to get the imaginary part, I get x minus x star divided by 2. And then I get an imaginary part. So if I rewrite the function this way, I mean this function should be equivalent with phi, which was the original one. Now, I can say, and I can prove, the proof is here, I can prove that the partial derivative of the function with respect to x, complex, is the partial derivative of the function with respect to the real part minus j times the partial derivative of the function with respect to the imaginary part. And this is the definition that we're going to use. Okay, this is, you know, the way to prove it. And the sketch is the following. Since the g, depending on real imaginary part, should be equivalent to phi, and this phi should be equivalent to a. So it's like a trick, you know. It should be equivalent to phi of x, okay, which is my function. So I can either, this is now the subdot, I can either consider real and imaginary part, or a complex number and its complex conjugate. Now, if I consider the number and its complex conjugate as 2 different numbers, then and I treat these 2 numbers as if they are totally different one another, and in fact it is, then I can find the correspondence. So, you know, by deriving, this is the derivation, okay, so calculating the derivative and then, you know, continuing on that, I get the proof. Now, some examples. For instance, you know, remember, we are in complex domain. So for instance, if I calculate the derivative with respect to x of x, okay, I use the definition, blah, 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 and what comes out is 1, which makes sense. If I calculated the partial derivative of x star with respect to x, now, x star is a new variable. Because, you know, there are 2 variables. I mean, in other words, x real and x imaginary are a way to represent x that is complex. Okay? But I can write as well x and x star. These are 2 numbers, okay, which is simply a combination of the complex values. These are another way to represent x, but x and x star has to be treated as independent variables. So since they are independent, when I calculate the derivative of x star with respect to x star is another variable. It should be 0. Now, when you put everything into the formula, which is the formula in the previous page, then blah, 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 you get exactly 0. So this is a consistent definition of the partial derivative. By the way, if I consider the partial derivative of the absolute value of x to the square, now the absolute value of x is x times x star. Because now, I mean, the absolute value is the number times the number itself and the complex conjugate. Then, if I calculate the partial derivative, then it is the derivative with respect to the first times the second, and the derivative with respect to the second times the first. Here it is. The derivative with respect to the first term, which is this one, and the derivative with respect to the second one, which is this one. Okay? But since the partial derivative of x with respect to x star is 0, then this is 1, then you get the x star. So, you know, these are, and then you can play with this. Now, our goal was to find the formula for the derivative. Now, let's consider, you know, the inner product between two vectors. We have a Hermitian x. Now, what does it mean, Hermitian? Do you know what is Hermitian? Hermitian is when you take a vector and you calculate the complex conjugate transpose. So, Hermitian means that this is a star, which is you compute the complex conjugate of the entry of the vector, and then you make the transpose. So what does it mean? It means that if you have a vector, you calculate a 1 star, a 2 star, blah blah blah, and then you calculate the transpose, which means you get a1 star, a2 star, and blah blah. So this is the meaning of Hermitian. So when you make it the Hermitian operator, it means that a vector is like a transpose, except that if it is a complex conjugate, if it is complex, you need to take a complex conjugate of the entry before making the transpose. So if I calculate now, in this case, and this is the reason why it comes in this way, because I have a vector which is a row, it is a1 star, a2 star, multiplied by, this is a row, multiplied by x1, x2. Okay? So it is row, column, and it is a1 star, x1 plus a12, x2 plus a13 star, x3 plus, and so on. Okay? So, you know, if I want to calculate now the partial derivative of a1 Hermitian x with respect to xk, so one value of k, then you apply the formula, okay, to the total set of the summation. When you apply the formula, you know, since you are calculating xk, so the only value which is different from 0 is xk. So it's the multiplicative factor with respect to xk. So it comes that it's only a k star xk that should be considered. All the others are 0. Because if I consider the derivative of, you know, with respect to x of a variable that depends on y, the derivative is 0. Okay? So that's, you know, I'm using trivial analysis. I don't know what it's calculated. Okay? So if I now apply this to the rule of a partial derivative to the overall vector, then, you know, I put all together a1 and 2 blah blah, which is a star. So at the end of the story, the partial derivative of a Hermitian x with respect to x, or here, it is a star. And this is a result. Okay, we keep it on the side. Then I can apply in a different way. So, I mean, I calculate the Hermitian with respect to x. Now, since this one, you know, there is a way. So since this one is, it is this x Hermitian A. Now, Hermitian has the same rule of transpose, except there is a computation of the complex conjugate. So this one, you know, is equal to, this one is equal to computing a Hermitian x, which was the one in the previous page, Hermitian. Okay? The previous page, you see? It's there. A Hermitian x. Okay? So here I have, so here I have Hermitian of A Hermitian x. So Hermitian of A Hermitian x is, now, it's similar to the transposition, except that there is a complex conjugate. Now, you can also write in this way. This is equal to A Hermitian x complex conjugate, and then transpose. Okay? Or you can either way, which is flipping. So it is A Hermitian X, transpose, and then complex conjugate. Now the second formulation is better. When you make a transpose, you are transposing, so you are flipping the entry. Now this is equal to X transpose A star. Then you apply the star, which is a complex conjugate to whole. Now, if I have a vector and I calculate the transpose, and then, after transposing, I apply the complex conjugate, this is the Hermitian. So this is equal to X Hermitian, and then A Hermitian, A complex conjugate, then complex conjugate again is A. Okay? Which is exactly the function that I was considering. So this one is simply the Hermitian of the previous one. So since we saw before that if I calculate the partial derivative for something that is Hermitian, then the result was 0, then this is what I expect as a symbol. Now I apply my formula before, and I apply on xk, similar as before, the result is 0, and all vector is 0. When I have a quadratic form now, so when I have X Hermitian AX, and now A has Hermitian symmetry. Now a new concept. What does it mean, Hermitian symmetry? Hermitian symmetry means that you have a vector, and then if you take the Hermitian of that vector, is the same. Okay? So this is the Hermitian symmetry, which is similar to the symmetry of a matrix, but includes also the complex conjugate in the symmetry. Now in this case, you can calculate, so you can use the formula that we used before, which means, if I need to calculate the partial derivative with respect to one entry, then what I do, if I have the derivative of the product, I calculate the derivative of the first, then I keep the second, then I keep the first and calculate the derivative of the second. Okay? So this is analysis 1, I guess, something similar. So this is exactly the same. So since I need to calculate the partial derivative with respect to a function that is multiplicative between two different terms, so what I do, I keep one term and I calculate the derivative for the second, plus I calculate the derivative for the first, and then I keep the second. So, but this and this, we already computed. So when I plug in blah 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 blah, okay, so what I get, this is blah 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 blah, okay, usually this means compute by yourself, okay, or verify. So, or go to the book in this case. I could not stack everything into a slide. Then what comes out that the partial derivative is equal to AX complex conjugate. So, and where this equality is because these are Hermitian symmetry. Okay? These are, the analytical rules. Now, before that, I need to say that if I write the same problem of regression for complex value of the signal, I should solve a similar equation as I did before. So I did yesterday, which is here, just to refresh it. The partial derivative were because I want to calculate a normal equation, which is something we exercise now soon after the break, is what I want to get because I want to become rich, because I want to find, the regressor formula, okay, for the stocks of today. Now, so, next step, next analytical entry, the eigendecomposition. Now, what is eigendecomposition? The eigendecomposition is a decomposition of a matrix into the constituents that are spanning the same subspace of a matrix, which is A in this case. Now, let's go slowly. So, What does it mean? I mean, practically. Practically is, that means that I have a certain matrix. Let's consider symmetric, okay? Or Hermitian symmetric, okay? Which means here, A Hermitian A, okay? Symmetric is A transpose is equal to A, okay? Now, so I have this kind of matrix. Then my goal is to compute the decomposition into the eigenvectors. Now, what is an eigenvector? Now, let me explain in a slightly different way. Suppose that you have a certain complicated system. Okay? Now, in this complicated system, if you touch the system in a certain way, and the output is exactly as the input, except the scaling factor, that input is an eigensystem, is an eigenfunction of the system that you are considering. So the eigenfunction, or the eigenvector, are simply a set of values that are perfectly matched with the problem, such that the output of this transformation is exactly as the input of the transformation up to a scaling factor. Now, let's see. So, let's see out of the word and let's see into the formula. Now, A is a transformation, so A is a matrix. So, A multiplied by Q is equal to Q. So, if A multiplied by Q is equal to Q, that means that, that Q has a particular shape. Because that set of value Q, remember, is a vector, so it's composed by a set of numbers. 3.5, 2.5, 2, 2, 35, blah, blah, blah. So if you apply this matrix to this vector, it comes out of the same vector, up to a scaling factor. Now, this vector is called eigenvector, Q, and the scaling factor, lambda, is the eigenvector. Now, you know the eigenfunction of a linear system. What are the eigenfunction of any linear system?
The slope. The slope.
No.
The exponential.
The
Exponential.
what exponential?
E forward to x.
No. You have a linear system. It's linear.
The power.
It's not a power.
The root of the transfer function will be the Laplace transform.
You are close to it. The sinusoid. No. The sinusoid are eigenfunctions of a linear system. Because if I take this table and I put it into vibration, okay, what I expect on the other side is a sinusoid on the same frequency that I put here, if it is linear. If linear. If it is not linear, that's another story. Okay? If it is not linear, then it generates harmonic. Perhaps I want to know these harmonics, but in general, if I have a system, then the system is analyzed according to the Fourier decomposition. So the Fourier decomposition is the eigenfunction. Some people call eigenfunction of a linear system the periodic sigma, which means if I enter into a system with a periodic sigma, with a certain period, 1 second, the output is a periodic sigma with a period 1 second. Okay, if you like, you can look at it this way. But these are eigenfunctions. Okay, so it's the periodic, it's not the same shape. So it's the period. So these are two eigenfunctions. And this is the reason why, let me show you, for instance. You see, I disconnect only because perhaps, I don't know, I have a photo of my kid, you don't want to see. Where is it? I want to show you some. This one. You might know this. This is a spectral view. Okay, Oh, what else you want? Here. Okay, this is a spectrogram. Okay? This spectrogram is making the Fourier decomposition. This here there is time, and on the other axis there is a frequency. These are the eigen decomposition of. You see? Okay? These are, I mean, these kind of plots are professionally important. I know you see in the disco, okay? It's nice, huh? When you go, you buy a music system, and there are all the lights that goes up and down. You enjoy. The more lights, the more money they make you pay, huh? Okay. Then you know, but it's also beyond that, okay? Probably you see this one, huh? Okay. Boom, 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 huh? But you know, I mean, this is a spectral analysis. So this one is an eigen decomposition analysis, because those frequencies are, you know, eigenfunction of the acoustic field that is traveling in the air. And this one is a vibration that is over, you know, the table. Okay? So the eigenvectors are not just a mathematical abstraction. Eigenvectors are practical. And you know, at the end of the course, you get a little bit insight on the flavor about the eigenfunction and eigenvector. Which means I want that you get a consolidated view. What does it mean, eigenvector? And every time you don't get scared. Eigenvector, you know, and then you get the desperate. Clear? Okay. So let's go back. So, you know, these are, so the eigenvector means I take any transformation. Now, this transformation can be a system. The transformation is I am exciting here with a sinusoid, and I'm measuring the sinusoid on the other side. I am exciting with the eigenvector with a certain vector. This is the table. Propagation of the table can be described by the matrix A. Now, you know, I mean, forget about the toy examples of matrices that are 2 by 2. The matrices that we are working with might be 1000 by 1000. Okay, is it clear? So you know, you will get the aptitude at the end of the semester, of course, that every time you see a problem, you try desperately to write in a matrix form. And this is, you know, another piece of the goal that I'm going to teach you, okay? To design, to approach, to solve a problem by using tools that are very powerful. Because once you wrote the problem in a matrix form, you go to your colleague that is an excellent algebraic person, and he tells you how to solve, okay? But don't give the problem to him, because they are going to pay him. So you keep the problem, you ask him. Huh? So now, Q, you see, A multiplied by Q is equal to lambda Q. Lambda is a scaling factor. Now this scaling factor is called, eigenvalue, and this Q is called eigenvector. Okay? Now, I can put together all these eigenvectors into a big matrix, which means this matrix A is A times Q1, A times Q2, A times Q3, and so on. Okay? I can rearrange all these eigenvectors into a big matrix. So these eigenvectors, you know, is one on the side of the other. And this eigenvector is the matrix Q. Oh, this is lambda. There's a missing form. Okay? Then you know this Q matrix is the matrix that contains all the eigenvectors. Now, very important, we will see in 1 minute why this matrix Q is so important. I try to give you the flavor about what is this matrix, what is the meaning for that matrix, and what is the meaning for lambda, the eigenvalues. Now, this one has a different way to represent. Usually, you perfectly know this. You see? Okay. Now, you perfectly know this. You perfectly know this. You totally don't know this. Okay? So now, since you know perfectly this, because probably you did in other class, Since you perfectly know this because you did in other class, I'm going to discuss this because you usually don't know, okay? Now, let's look together. What does it mean? That representation, that one, is a very classical decomposition that is also usually used in image processing, for instance. Now, that is called a rank 1 sum of eigenvectors. What does it mean, this word? Let's read it together. I'm working on this one now. Okay? So I rewrite the matrix A as a sum of lambda K, QK, QK transpose. Now, what does it mean this? Okay, this one is called the outer product. Okay, so this one is, now I isolate one term, okay? So that one, which means, it's lambda 1, Q1, Q1 transpose, plus lambda 2, Q2, Q2 transpose, blah, 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 okay? Now, each one of these terms is one vector, Q1, multiplied by one vector Q1 transpose, because it's one is vertical, the other is horizontal. Okay? So, what does it mean this one? This one means that this matrix, okay, is a matrix that this comes a matrix. Because this one is it's n times 1. And this becomes 1 times n. Okay? So in total, the output becomes a matrix that is n times n. Now, look what's happened. Imagine now that the behavior of this eigenvector is, is like this. Okay? Now, what's happened? It happens that this vector is smeared in this direction. Smeared means that, I'm copying this one, this behavior, in this way, and scaling. Okay? I'm smearing, which means, if I look in this way, I can see, like, a pattern. And the pattern that I can see is coming also from the other behavior. So I can see like two different crossing of shape. The crossing is perpendicular one with respect to another. It's like the old city, Roman city, because there is the Cumano. There are two roads that are crossing this way. All the others are perfectly crossing. Perpendicular one with respect to another. Okay. Now this matrix is a rank 1 matrix. Now a rank 1 matrix is a matrix where every column or taking two columns, they are totally linearly dependent one with respect to another. So a rank 1 means that there is only one column that is linearly dependent. The others are totally dependent with respect to the first. It's obvious, because if I take the second column is the first multiplied by this number. So the first column is this multiplied by this number. The second column is this multiplied by the second number. So since every column is multiplied by a number, there are never two columns that are linearly independent. Then, there is just one. And this matrix is rank 1. So this one, it can be written as a sum of matrices. N times n. Lambda 2, blah, blah. N times n. Each one is rank 1. Each one has the property to be smeared in this way. Now I, write a note and do use MATLAB. Choose any arbitrary matrix. You're better to take a minute. But choose any arbitrary matrix. Make it symmetric. Okay. So by MATLAB, you open MATLAB. Okay. You take a matrix. You make a matrix that is A that is symmetric. Okay. One trick to make a symmetric matrix. Okay, you do this way. You generate any matrix. You take that matrix plus the emission of the transposal matrix divided by 2. That is symmetric. Okay, that's a trick. So, a stupid trick. You generate B as you wish. Okay. Generate B as you wish. Then you make A is equal to B plus B transpose divided by 2. This matrix is symmetric. Okay, because I build as a symmetric one. Because if I make a transpose, it's equivalent to itself. Okay? So now you take this A, you compute by MATLAB. Okay, you generate B as you wish. I don't know, you generate as a random. Okay? So if you want to generate as a random, make a random. You make an N. Okay, this way B is generated as a random number. So you don't get crazy. Okay? You make this trick. Okay? And this way you get a symmetric matrix. And then you calculate the eigenvector, which is the instruction that, the MATLAB instruction is A. Coming out from A, so you calculate A from A, and you assign A to Q and N. Okay. So Q matrix contains all the eigenvectors, and the lambda contains all the eigenvectors. Okay. Then what you do, you take this one, you extract. So what I'm doing here is extract one eigenvector. Anyone, the first, or the second, the third, or whatever. Okay. So I copy Q equal to capital Q. I don't know. It's the number 3. Now in MATLAB, capital Q bracket 2 points, comma 3 means take all the entry along the column. Okay? And the third position. So what I did here, I have a big matrix here. This is the matrix Q. So I choose the third column. Okay? And then I assign this one to this is what is implicit in this operation. Okay? After you have been doing this, you do a plot. So you do this kind of image. So this kind of image is done this way. You make after this. So this is a sequence of MATLAB instruction. Huh? So this is the generation. This is the eigen decomposition. This is extraction of one vector. Then to make images. Okay, images is making the picture, so like a photo of what? Of a matrix. Okay? So any picture is a matrix. Huh? Is a matrix is not a matrix of pixels. It's a matrix of numbers. And numbers are mapped into pixels. Okay? Don't confuse, the cause with the effect. Now, so, images is generating the picture. Okay? And the picture is generating by making the outer product, which is this one. So I make a Q. Now, in MATLAB, the transpose is made by the prime. And you see the picture. Okay? So if you like, I keep this on the board and then we will do in 1 minute. Okay, it takes less than 1 minute, probably around 30 seconds to make it. So then you will see what the effect that I'm talking about. Now, so that means that any matrix can be decomposed into a set of matrices. If we were in an image course, I would say any image that can be decomposed into a combination of rank 1 images. And usually those rank 1 images are used for the classification or recognition for faces or symbols. Okay? So using, some pattern recognition methods. Now, beyond that, here is the rank 1 decomposition. So, to conclude this part, this representation is more useful for us than the representation which is on above. Okay, the others. Now, the other property is that the eigenvectors are orthonormal. What does it mean? Orthonormal means is orthogonal one another and normal. They are normalized. So this is the meaning. Now I can either consider the orthonormal representation as in this way, or the other. I mean they are fully equivalent. So if I write a Qi transpose Qj, this is the inner product. Or scalar product. Okay. So this is saying that if I make a row vector times a column vector and these two eigenvectors are different, the result is 0. If I'm using the same, the result is 1. So that means that since the result is 1 when it's the same, I can, let me see, I continue here. So what I can say is that since Qi Qj transpose is equal to 0 when I is different from j, this means that I have a vector Qi times a vector is Qj, and this is equal to 0. Okay? But if now this is I, then I have a Qi in red color, then this one is equal to 1. Okay? In numbers, if I use numbers, this means that the sum of Qi is vector k. I indicate it this way when I take a vector and I extract the one entry. So the kth entry to the square, k going from 1 to n, this is equal to 1, which is the norm of the vector. So the norm of the vector is 1. This is the reason why they are called orthonormal, because they're normalized because the norm is 1. Some aspect. One property that we need is that the inverse of a matrix that is decomposed can be calculated in the following way. Now let's prove it. Let's spend a few words to prove it. And entry in a new page. So if I make Q, so if I consider A is equal to Q lambda Q transpose, okay? And I know that the Q transpose Q is equal to identity. Now my goal is to calculate the inverse. What is the inverse? The inverse is a particular matrix B that I multiply by A and the result is identity. Okay? And I will call this B, I will call it A to the minus 1. the inverse. Okay. Now, how do I make it? So that means that if I want to calculate the inverse, then I make the eigendecomposition. Now B multiplied by Q lambda Q transpose is equal to the identity. Okay. Now let's multiply left and right. So let's replace this identity by Q transpose Q. But now, since the eigenvectors are orthonormal, that means that Q transpose Q equal to identity. So this Q transpose is the inverse of Q. Okay? So Q to the minus 1 is equal to Q transpose. Because what is the inverse? It's a matrix that is multiplied another that is equal to identity. So, I can multiply left and right now, okay, by Q. Now, if I multiply left and right by Q, then what's happening. So I have B, Q, lambda, Q transpose, okay, which is equal to Q transpose Q. But then I can multiply by the inverse. Now, if the inverse of Q is Q transpose, the inverse of Q transpose is Q. Okay? So the inverse of Q transpose, so I multiply by the inverse, which is here, is Q. Okay, so I put Q here and I cancel there. Then I multiply, I want to multiply by Q, and the inverse of Q is Q transpose. Okay, so and Q transpose, goes on the other side as Q transpose because it's the inverse. Okay. Now, but this one is the identity. Okay. So, I have that here in this case. Okay, I have a Q. Q, B, Q, lambda equal identity. Okay. Now this lambda is a vector of numbers. And so since this lambda is a vector of numbers, then I can move to the other side. Then when I move this lambda to the other side, it becomes lambda to the minus 1. So I have a Q, B, Q equal to lambda to the minus 1. Then I make it back at the same steps to isolate the Q, and then I get the results. Okay, so I iterate the same operation. So I multiply left and right by Q transpose, and then I get the result. Now, so this means that if I need to calculate the inverse of a matrix, the inverse of the matrix is simply calculated by the inverse of the eigenvalues. So the inverse of the eigenvalues is obtained, is calculated, so is giving the inverse of the matrix. So if the eigenvalues are close to 0, then the inverse is unstable. Then when the eigenvalues are very close to 0, the inversion is impossible. Now, perfect. How can I do it with that? Now, let's make one example on the eigendecomposition. Let's consider a practical problem. The practical problem which is called the power control. What is a power control? The power control is a configuration that is used in the industry, mostly in the wireless system, to control the power transmitted by different devices. Okay? But now, let's make a very generic and more pictorial. Let's consider the case where, it's not cells, but these are tables. So I have a table number 1, table number 2, table number 3, blah, blah, blah. And in every table, there is a certain conversation. Okay? So the power that each table is transmitting is, you're talking with your other people, okay? You have a certain volume, right? So every time, you know, that you are talking at a table, you are interfering with the others, and the others are interfering with you. So there is a certain attenuation between your table and the others, okay? So let's consider this attenuation as a Gij. So, you know, Gij is interference between the level of the attenuation part, which is, you know, going from I and J. So if I am transmitting, for instance, if a certain table like here, we are using a level of volume which is Pj, okay, this is the volume in this table, then, you know, we are interfering in the table I by a level which is Gij multiplied by Pj. But since all the tables are interfering with this, I can calculate the degree of interference, because, you know, it's a level of noise, which is a result of the mutual connection with the other tables. Now, so, you know, I can calculate the sum, the total interference at here. So the total interference, you know, that I get is the sum for all the tables except myself of the power generated by the neighboring tables multiplied by the attenuation of the signals from that table to me. Okay? Because I'm sitting on table I. So all the other tables are interfering to me. Yeah? So this is the level, the total power of interference. Now if I want to talk easily with the other people, I prefer, I mean, ideally I would have this term to be 0. Okay? Impossible. Huh? So that, I mean, the level of interference depends, the level of voice depends on the culture, okay? So if you go in, I don't know, in a very expensive restaurant, the people are not shouting, okay? But if you go in a pizzeria, they start shouting, okay? So, you know, it depends. Huh? So the more you spend, the better you stay, usually. That's a good reason to gain money, right? Okay. So now, let's write it. Now this problem, the telecom people, they know perfectly, because this is a problem of power control, and these are called cells. And this is different cells that are allocating the power to their own users. But, you know, let's stay on a very generic case where, you know, we have a conversation among tables, right? Okay, so, I mean, what I want is that the SNR, what is the SNR? It's the power of the signal with respect to the power of all the interference. So the power of the signal with respect to the power of all the interference should be larger or equal to the certain threshold value, which means the tolerance value. So in order to be relaxed, I want that all the level of interference should be lower than a certain level. Or I can write it this way. The power of the signal, this is the power of useful signal, and that is the power of total interference. Okay? This is larger than a certain value. I don't know, 10. Okay? So which means the power of the people I'm talking my table should be 10 times larger than the noise. Okay. So where is the matrix? Right? I mean, you already see it, but, you know, I mean, in practice, I would say, where is the matrix? So now what I do this way. I mean, I write this problem for all the users. So if I write this problem for all the users, and I reformulate it this way, which means I move this one on that side, okay? So when I move this part of the equation on the other side, it comes this one, which is the one that I'm going to use. Now, when I rewrite everything in this way, I write in the matrix form. Now, writing in the matrix form means I write for every user, so I have n tables in my restaurants, okay? So for every user, I write the condition of gamma. Gamma is the degree of SNR, or signal to interference ratio, that I tolerate, okay? So it's a minimum. G is the attenuation factor, okay? So then I write the matrix, which is G, okay? And then here is the power. The P1, P2, blah, blah, Pn is the power in every table, okay? I want that this one is lower than the set of vector powers. So I came out with this kind of equation, okay? So what I want, we will do this later, right? They're right here. So what I want, okay? I want that, you know, as written there, I have a D, then multiply by G is the gain, then is the power, a vector power, should be smaller or equal than P. My unknown is P. So what is the power that I should set all the tables such that this inequality is guaranteed for every user? So every table is happy. Okay? So this problem is called the power control problem, which means what is the power that I should allocate every table such that, okay, such that, you know, every table is happy. Now, it's complicated to write inequality, but rather than writing inequality, okay, I'm going to write equalities. So the equality can be this. I can write this way. D multiplied by G, multiply the vector P, multiply by a scaling factor rho, equal to P. And I constrain the rho to be smaller or equal than 1. These equations, the upper equation and the lower equation are the same. But the second one is more manageable. Okay? You have not recognized it. Huh? Now, if I write this one as A, so it is A times P equal to 1 over rho times P. What is the solution? Solution is the eigenvector of A. So if I can find the eigenvector of A such that the eigenvalue, now is rho the eigenvalue. Actually the eigenvalue is 1 over rho. Okay? Such that the eigenvalue, so if that the rho is smaller than 1, that means that should be larger or equal to 1. Such that the eigenvalue is larger or equal to 1. That is the power all the people should fulfill when they are sitting in each table, such that everybody is happy. So we found a way. By the way, you know, it's very strange, okay? So the solution is one eigenvector, okay? So I gave you one very simple, practical, intuitive example, where, you know, the eigenvectors are solving a problem. Now you say, now it comes a common comment, so, you know, so fulfilling this comment. I say, but you know, when I'm in a place, the volume starts growing. Okay, exactly. Because, you know, this equation is fulfilled up to a constant. Okay? So, you know, if I take a if I take a P, the power, okay, which is the unknown, has a certain behavior. So, these equations say, P1 should be like this, P2 should be like that, P3 should be like that, but you know, if I multiply left and right by a constant, the solution is still the same. So this constant is creating trouble. Because, you know, it's enough that one person is rising up the volume, all the others are trying to adapt, all the others are intuitive, they are naturally moving to find the eigenvector of the table system. So once the other rise the volume, at the end of the story, you know, you are rising the entire volume. Now it's enough that one person rise up, and then everybody rise up, everybody rise up, and then, you know, at the end the people are shouting. In fact, look, if there is a noisy place, you say, shut up! Then it goes down. Then after a while it grows up, but you know, if you put in the center of those set of tables and you try to notice, they balance is always the same, which means there is always a set of people that are shouting, a set of people that are quiet, and so on. So, which means they are corresponding to the eigenvectors, and the eigenvectors, the value of the eigenvectors are always the same. So there are something which is in the next blah blah. So there is a Gaussian theorem and so on, but it's something that we don't use it. So that is a very nice exercise to see. Now, this is another case where you're better to know what is these eigenvectors. It is the so-called quadratic forms and the diagonalization. Now, when we try to solve, and we will do now, soon after this lecturing part. I mean, when you solve it and you try to solve the quadratic form, what you want, you want to solve it because you want to get a solution. But it's better to understand how is this quadratic form. So you cannot solve the problem if you don't understand the problem. Because they don't pay you because you solve the problem. They pay you because you solve the problem, you are the expert. And being an expert is not giving the equation. Being an expert means knowing the problem, knowing the solution. So let's move to the issue. Now, quadratic form, okay, is x transpose Rx, and you remember, okay? The quadratic form means that, I have something like R11 x1 square plus R12 x1 x2 plus R13 x1 x3 plus blah blah blah. Okay, maybe. This is a quadratic form. Now, the quadratic form can be also written in a second way. And the second way it can be written is this one, as a trace. Now, what is a trace? You are now, I'm introducing the different operators, one by one. But don't be afraid. If you don't remember these operators, these will enter into your daily usage slowly after, time by time. So, what is a trace operator? Trace, if I calculate trace of a matrix A, means that, I have a matrix A, which is A11, A12, A13, blah blah, A21, A22, and so on. Trace is the sum for this. So it's the sum of all the entry along the diagonal. Okay? So which means the trace of A is the sum, so it's A11 plus A22 plus A33 plus blah blah. Okay? This is trace operator. It's calculating the trace. Now, or I can write it, which is the same, I can write it as sum of I from 1 to n. Okay? This is the trace. Now, the trace operator has a very nice property. And the property is the following. Okay? So the property is this. If I calculate the trace of A multiplied by B, the property is a circulant property, which means, the trace operator is the same as if, if I take this matrix and I put there. So the trace A multiplied by B is equal to the trace of B multiplied by A. And and if you have more than 2, it is a circular. So it circulates around. So if I calculate the trace of A, B, C, okay, so I can rotate there and put there. So it's equal to the trace of C, A, B. But this can go there, which is equal to the trace of B, C, A. And then keep on going, okay? So if I apply this property to the quadratic form, which means, I can rotate one way or the other, and the property remains the same. So since this one is a scalar, I can calculate the trace of x transpose Rx, which is the same as trace of Rx x transpose. Because I take this and move it to the other side. This is the equation which is indicated here. Now, let's consider the quadratic form, the generic quadratic form, which is the quadratic form that we use for, you know, the regressor, okay, so for the learning problem, okay. So let's consider, you know, that quadratic form. Do you remember? It's only a different notation. We use the theta, I think, I don't know, it's here. Let's see. We use the theta, here it is. Okay. We use theta transpose R theta minus 2 times P transpose theta plus the J0. Okay. You remember the problem was to make a regressor on the stops data. That we will do now. Okay, so you know, this is the quadratic form. I told you it's a quadratic form, but you know, we need to get a little bit knowledge about that. Now, let's go back. So let's consider any arbitrary, generic. Okay, so I have a quadratic form phi of x. Now the variable is x instead of theta. Okay. Don't get stick on the variable. I can call it Giovanni, Francesco, I can call theta x. Okay, so still a quadratic form. No? Don't be confused. You are not kids, so you are old enough. So this is a quadratic form in x. So I have x transpose Rx minus 2p transpose x plus a phi 0, with phi 0 known as scalar factor. The matrix is symmetric. You know, since it is symmetric, we know that for a symmetric matrix we can calculate the eigenvector. Now, my goal is to find the minimum. So I calculate the derivative and I use the formula for the derivative. Okay, so if I want to get this one, use the derivative. Okay, this is why I made you spend so much time to talk about the derivative rules, because you need to know how to calculate that. So the minimum, this is x minimum. Perfect. Now we know it. So if I want to know what is the value at the minimum, then what I do, I plug in this into the formula, and then I get the value at the minimum. The value means, you know, if I have a function of x, I want to calculate the minimum, then what I do, I put the derivative to 0, then I get the position of the minimum, right? If I want to see how much 8 is the minimum, then I just take the x value and I put into the function. This is what I did. So if I do this one, blah, blah, this is the results. Now, let's gain a little bit insight. So let's understand a little bit. So this quadratic form is indicated in this way. So it's a ball, okay? We saw yesterday, you know, we wanted to go down to the hill through the ball, okay? Actually, you know, we were very, we dared to go down. We don't know exactly if we were going down or not, okay? Technically, you know, this is the issue. Now what I can do is the following. Look at, this is the parabolic shape. Remember, in this picture, you know, I'm assuming that the size of x is 1. Okay, so the problem is 2-dimensional in x. So n is equal to. But as I said yesterday, you know, might be multidimensional. Okay, so I can only sketch 2. Now, let's consider. So let's look at this one. This one are the contour line. The contour line that comes because, you know, cutting surface in a different way. Okay, it's like to go to the mountain, you know, to see the contour surface. So this is my axis. So my axes are x1 and x2. Now I know where is x minimum, x2 minimum. So I know the position of the minimum because I computed it. Okay? So what I can do, I can take my axis and I translate my axis to refer to the minimum. So which means I put my origin, okay, from here to there. So if I put the origin there, which means I translate it, okay, so that means that I need to define a new set of variables. And these variables are y, y1, y2, okay? So y, what is y? Now y vector is equal to x, okay, minus x minimum. I translate, okay? Okay, now, let's see analytically. So if I translate, so this is the translation, the formula for translation. So if I translate, and I plug into the quadratic form of translation, what I get is a quadratic form where, there is only y transpose r y plus feminine, which means the linear term disappears. So conclusion number one, if in a quadratic form I have a linear term, that means that my quadratic form has not the origin into the minimum, but the origin is a little bit misplaced. Okay? Second, now, since I am now, my axes are this one, y1, y2, okay? So which is in red. And my quadratic form, can be sketched, okay? So this is my quadratic form here in red, because the axis is red, depends on y. So it is y transpose r y plus the minimum. Okay? Which makes sense, because if I put the y equals 0, then I'm in the minimum, right? So that is the minimum. Now R, matrix R, is symmetric. Then I can calculate the eigenvector, eigenvalue decomposition. So let's make it. This is the second step. So as a second step, what I do, I can calculate the eigenvector, eigenvalue. Now, so that means I noticed that, the lambda cannot be printed. Sorry. Here, there's a lambda here. Okay, so, the second step is, in place of R, I calculate the eigenvector decomposition, okay? So rather than call Q, I call the U. Okay, instead of Giovanni or Maria, but they are still eigenvectors. Okay, now, so this is R. So now what I can do, I group, I pair, okay, now, the eigenvectors with the vector Y. Okay, so which means, what I do, let me say, I take the bracket and I pair, I put together, okay, different pieces. So I have a U transpose Y, and here I have a U transpose Y, everything transposed. Now this new variable I call Z. But what is a Z? Let's write here. What is Z? Now, eigenvectors. The eigenvectors, here it's in 2 dimensions. So the eigenvectors are 2 vectors. But these 2 vectors are unit norm, by definition, okay? And they are orthogonal one another. Because every eigenvector is orthogonal to all the others. So if I make a 3-dimensional case, it's like to have 3 vectors in this way. They are orthogonal one another. We call versos probably, okay? Which are unit vectors, okay? So they are orthogonal one another, and these are describing these space. Now in this case, the 2 vectors are describing the b-dimensional space. And, if I have 3-dimensional, it's 3-dimensional space, and then it's multi-dimensional, depending on the case. So these are U1 and U2. Okay? Now let's look at what's the formula. Z, okay, in this specific example, is composed by two parts, Z1 and Z2. Now Z1 is equal, example this column, is equal to U1 times X transpose. And Z2 is equal to U2 transpose X. So if X is here, okay, Z1, if this one is X, Z1 is simply, calculating this length. And Z2 is simply calculating this length. So Z1 and Z2 is the component of X onto the two-dimensional U1 and U2. Okay. So in practice, what's happened? It happens that when I define Z1 and Z2, what's happened is that I rotate now my system, my reference system, with respect to the two eigenvectors, so that the Z1 is along one direction and Z2 is the other direction. And now my elliptical surfaces are oriented along the two principal axes, and these two principal axes, principal axis 1 and principal axis 2 of the ellipses, are perfectly oriented orthogonal one another, and are oriented with respect to the axis Z1 and Z2. So what I did, by multiplication with the U1 transpose, I rotated the axis. So the two steps are, step number one, I translated the axis. Step number two, I rotated the axis. Translation is to put yourself into the minimum. Rotation is to put yourself into the principal axis of the elliptical surface, the elliptical contour line. So when I evaluate, my problem, let me say, with respect, here is lambda. Sorry, but it's printer problem. It's a font problem. Okay. So when I write my system in this way, then what I can write is in this diagonalized form, which means it's lambda 1 and Z1 square plus lambda 2 Z2 square plus blah 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 plus lambda and here Zn square. Okay. So what's happened is that in this case is only Z2, but in the general case it might be up to the dimension of the problem. So what happens is that in the quadratic form it disappears the mixed term. So there is no more x1, x2, x1, x3, but there is only the terms that are dependent on the square of the variable. Now the quadratic form has been diagonalized, which means it depends just on the quadratic of the values. Now it's important because if you look at the problem, that means that these axes are the so-called principal axis. So there is a very convenient representation. If I calculate the second order derivative of this system, the second order derivative is equal to the lambda. So if I calculate the second order derivative with respect to Z1, I get 2 times lambda 1. So this means that lambda 1 is proportional to the curvature of the quadratic form. Now, in this case, assume that this axis is lambda, this axis is Z1, this axis is Z2. So, if I calculate the derivative in this direction, okay, so what I see is that, I get the lambda 1 as a curvature. And I calculate the second order derivative in the other direction, I get the lambda 2 as a curvature direction. So that means that here lambda 2 is larger than lambda 1 because it's steeper. So from this example, I obtain that, lambda 2 is larger than lambda 1, because, the curvature, the corresponding curvature is larger along the direction z2 with respect to the direction z1. This aspect is very important when you want to go down, because remember, we want to solve the problem iteratively. And if we want to solve iteratively the problem, then we start from one point and we go down. But if the problem is this way, then I might be slow to reach the minimum, because I keep bouncing. Because one eigenvalue of the quadratic term r is much larger than the other. And for this reason, my solution might be bumping. It doesn't go straight at the minimum. So it's like a ski, when I ski, I try to go to the minimum, but then when I ski, I look locally and then, it says, okay, you want to go to the valley is there, but you don't know the valley. Then you calculate the gradient says, okay, the maximum steep is there. I take the negative, go there, and then I know, rather than, sliding and then stop at the minimum, then I keep sliding and then I move higher. Then I slide again, then I slide again, then I slide again, and so on. And I reach the minimum with oscillation. So I don't reach straight the minimum. It's take more time. Okay, this is the concept. We touch this aspect later. So we make a break and then we manipulate the data by matter. Okay, very good.